Welcome to video number 4. This video will be on the input characteristics and the output characteristic op-amps. First, we'll be talking about the input characteristic of a non-inverting because these are easy. Okay. Here's a schematic of the non-inverting. Your stimulus is on the non-inverting input. And what I like to do is I like to insert the MOSFET model. And this is the MOSFET model that I like to use. It's a voltage control voltage source. Here's your VD minus, VD plus, and here's the voltage source. So this voltage will amplify the differential between the VD plus and the VD minus, and it will multiply times A sub naught, which is the open loop gain. Okay, so in this first analysis, what we do is we unhook your source, or actually we can use the same source, but we're labeled it instead as VT. VT is a test voltage. Okay. And we can always assume that it's like 1 volt. And if you put 1 volt, then it's going to generate IT. And that's your test current as well. Okay. So if you can tell right here, you have a voltage, and if you have current flow, you will have current flowing in this direction. However, we said that the input characteristics, or at least looking into the op-amp, is infinity. So that's another, or let me restate that. We can say that the I bias is equal to 0. Okay, let's say that it's there. Okay, so since your bias is 0, okay, basically you're gonna have a VT over IT, and since there's no current flowing through this resistor, so basically, let me backtrack. Since your I bias is 0, that implies that your IT is 0 as well. And as IT goes to 0, the VT IT goes to infinity. Okay. So basically your input impedance on a inverting is infinity. Okay. Now we can also do the same thing with the output. We can put a test voltage here, T, that generates a IT. Okay, but you have a voltage source here, and anytime you have a voltage source, you assume that it's shorted. Okay, so since it's shorted, by inspection you can see that the VT IT, and I'll put output, is equal to 0 ohms. Okay, so we got that. Here's the input, and here's the output. Okay, next is the inverting op-amp. got the stimulus going in at the inverting side. We're going to place the VT and IT. Now what I did is I did some of the math because it was a little bit long and didn't want to spend too much time, but at least you'll be able to see the equations. But this is how I set it up. What you want to do is, once you have your VT and IT, you do a, let me see, you do the Kirchhoff's voltage law. Basically, you sum these voltages. You got a plus, no, minus, plus. Current is flowing in this direction, and then you have a plus to negative. So you sum this current, or the voltages rather. Let's take this green. So you're going to write an equation that involves VT, ITR1, ITR2, and then V out. So that's the loop. That's that. Okay, which is equation 1. So you got VT minus ITR1 minus ITR2 minus V out. Okay. Another important in setting up the equation is, how do you define V out? And V out, you can define it as the differential voltage, or actually this here, which is VD plus minus VD times the open loop gain. And what you do is you insert that right there. Basically, you substitute equation 2 into 1. Once you do that, if you notice, it's right there. So we have this third equation. Okay. The next is this here. You need to define VD because you have this VD here. So if you look at the schematic, VD, well, VD is actually this voltage, VT, times this ITR1. So basically that's what this statement is, number 4. Okay, so basically we subbed 4 to 3. Basically this VD is going to go there. And that's where, see it right here. I'll label this as equation 5. Okay, and then we distribute, and then we have this equation, and once we have that, we solve for VT over IT. So we're down to this equation. So we separate them. Okay, bring this over and bring this over, and we have this there. Okay, now what we can do is we can break this into this equation, and you'll see why. Okay, now once you have it in this form, you can see that when A sub O, which is the open loop gain, when it goes to infinity, this gets large. So basically this goes to 0. Same as here, A sub O goes up to infinity, that goes to 0. Now if you look at this term as A sub O divided by 1 plus A sub O, it actually goes to 1. So basically it's R times 1 equals R1. So all of this equation is equal to R1. So if you look in here, basically all of this equation is saying that the input impedance, looking in here, is this value. Why? Well, the equation says that it is, but remember we said that this node, because IB is 0, that means that the voltage at this node is 0. And then we made an assumption or statement that said that if VD plus and VD minus are equal, so if they're equal, that means that this is 0 volts. And we even said that this is called virtual. Let me rewrite it. We said that this is virtual ground. Basically, you can ground. It's an artificial ground. So if you put your source here or your impedance meter, you'll notice that that's the impedance. Okay. Now remember that is true if A sub O is high enough. But what if A sub O is not high? Let's say that you have an A sub O of 5. Okay. Well, the equation that derives is pretty handy in that I have a condition here where A sub O is 5, and we have a resistance of 10K, 10K, and like I said, A sub O 5. So just plugging in these numbers, well, we get 10K over 6 plus 10K over 6, 10K times 5 over 6. And we'll figure out what the equation is, or the answer, in a little bit. But what we're going to do is we're going to do a little bit of spice. Get the answer first, and then we're going to come back and see if it's correct. So we're going to go to spice, and here I have top spice. Okay, go ahead and take this resistor off, and let me explain a little bit about the circuit. This is a voltage control voltage source. Here's VD plus, here's VD minus. Now if you notice, there's a plus here. In our model, the plus is up in this, it's up on the top instead of the bottom. So to get around with this, the gain that we specify for the voltage control voltage source, to make sure that the signs change, we say that it's a negative. Okay, so we'll go ahead in the example that we're using, we're going to use a 5. So we'll put a negative 5, and remember the negative 5 will mean that the plus will be up in the top and the minus will be on the bottom. It flips it basically. Okay, so we have a 10K for R2, a 10K for R1, and we know that if the gain is very high, then the input impedance looking in is going to be 10K. Okay, now this resistor R3 really doesn't have any bearing on it. It can be actually go to ground, it can be any other impedance. It won't affect the value that it sees on the inverting side. Okay, now here's another great tip. You can use SPICE to calculate your input impedance and your output impedance, and also the gain of your circuit. If you remember, the gain is supposed to be, since it's an inverting, is this resistor divided by this resistor times a negative. So basically it's negative RF divided by RA. Usually I call this RA. So in this case, since they're equal, we're going to have a gain of negative 1. Okay. Now to do that analysis, we go to simulation, we go to setup, and you should have something very similar on whatever simulator you're using. This happens to be TopSpice, and it's very similar to PSpice. You should have a DC bias point. So I'm enabling the operating PC point, and right here it says transfer function calculation. This will calculate the gain that you have from the input to the output, but it would also calculate the input impedance and the output impedance. So all you have to do is specify where it says input source, you put V2. That's this source. So you define it right here. And then the output variable is what node do you want to take the measurement from. So in this case, I type in V out. Okay. Once I do that, go ahead and run it. Okay. So then we have to look at the output file. This is the output file or the text that TouchSpice, and also PSpice should have something very similar. And in the text file, it has the net list, and it has a bunch of useful information. It has the voltages, and then if you keep scrolling down, here it is. Here, go ahead and copy it. Okay, and we'll come here and paste it. Okay, so now we have the answer. So let's see what we get. Excuse me. So let's get the calculator. Okay, so it's 10K divided by 6 equals, so this should be 1, let's see, I forgot what it was. Okay, 1666.66. 6 plus 1666.6. Okay, and the last should be, let's say, it's 10K times 5 equals divided by 6. Okay, so we're gonna go, let's see, here it is, plus 8333.3, I believe. Yeah. So let's see, where's my question? Here it is. Okay, so I'll go ahead and write this like this. 666.6 6661. Okay, so this is 12, 13, 14, 15. It's 12, 13, 14, 15, 16. This is 12, 13, 14, 15, 16. 12, 13, 14, 15, 16. 9, 10, 11. So the answer is 11,666. And if you look in here, it's a match. Okay, so basically it's 11,667. They rounded off. And if you look in here, our output is 0 ohm, just like we had mentioned up above. Now you may have noticed I had made a statement that the gain should be a -1. Okay, it should be a -1 if A sub O is high. Okay, let's go ahead and take a look, see if it does turn out to be -1. Go back. Let's make this high, and high I mean, let's say 100K. We run the simulation, Close this. Okay, so if we do have, and if you notice, right there it is. Gain is that. Paste. Okay, so in this case, the gain was not as high as we expected it initially because we had an asable of 5. But once we have an asable of 10K, then we got the gain that we were expecting. And this was because it's supposed to be RF R1, which was 10K divided by 10K. Okay, so in a nutshell, that's the way you calculate the input impedance. And we did a rigorous proof. And if you have this in the test or take-home test or exam or homework, you'll be able to derive it with no problem.